Hello and welcome back to another HFSS tutorial. In this video, we'll be continuing with part 2 of the design and simulation of a 5.8 GHz microstrip patch antenna. In the previous video, we used the antenna toolkit to create the system, while in this video, we'll be using textbook equations and formulating each part from scratch, culminating in the simulation and data comparison between the toolkit antenna, our version of the antenna, and a fabricated prototype. Without any further ado, let's get started. To begin, we'll go over some design choices and then the dimensions calculated from design textbook equations. We'll be using a Rogers 5880 laminate with half-ounce copper. The datasheet states that the relative permittivity is 2.2. We'll continue using the center frequency of 5.8 GHz for the design. From the board manufacturer's physical limitations, the smallest inset gap that we can achieve is 0.0275 centimeters. That's what we'll be going with. The board dimensions we're simply choosing to be 10 centimeters squared, and then the board thickness is the standard 1.575 millimeters. Standard textbook equations can help us arrive at a set of values to dimension our patch antenna, but inevitably they all require tuning to achieve the design goals specific to our requirements. So I've listed a set of equations that help us arrive at initial values, but most of these, especially the length and inset distance, have been tuned and adjusted during the first design of this antenna to achieve results that were optimal for our requirements. So we'll be going forward with the dimensions highlighted and bolded there in the design going forward. So here we have ANSYS HFSS open. This is the completed model of the patch antenna, including substrate, ground plane, antenna, and even an SMA connector that we've downloaded from the manufacturer's website that we can include in our model to increase the fidelity of the simulation. So as stated, we'll be doing everything from scratch and aiming to make it as similar in appearance to this model. And the first thing we'll need to do is create our own new project. So now we'll go ahead and create a new project, and in that project we'll insert a new HFSS design. So now we have a blank canvas wherein we can create our own patch antenna from scratch. The way we'll be using the dimensions is through the design properties feature of HFSS that can be accessed through the drop-down menu and at the very bottom, design properties. This basically allows us to input these numbers and dimensions as variables that we can change later on, and it'll propagate through our entire design, simplifying changes if we need to make them, such as during the tuning phase of an antenna design. So to add a dimension, all you have to do is hit add. Let's say we want to add the width of the patch antenna. We can just name it width of patch. And then all we have to do is type in the value. It's 2.04 centimeters. I'm going to include the units here with the space and hit tab, and it'll auto-populate the unit type and units fields here. You hit OK and it's been added to the design. I'll spare you some time and go ahead and fill out the rest of these dimensions, and then I'll be back. Alright, I've inputted the rest of the dimensions into properties in HFSS, and now we can go ahead and start putting elements into our model and constructing our patch antenna. Let's go ahead and do that. So in creating really any object in this design, what we'll do is first create a rough sketch using the simple commands over here like draw a box and draw a rectangle, and then we'll dimension and size them accordingly so that we can get the antenna we want out of our design. So for the substrate, I'll go ahead and draw a box. If you're not in this mode where you have a cursor following you, you can hit F3 and it will change modes for you. Then we can click and drag and just define a simple 3D box with 3 clicks, and then now we're able to dimension it ourselves. So this box is currently much too small. We see it's about a few millimeters wide when we wanted it to be 10 by 10 centimeters. So if we change the create box command by double clicking on it, we can change its initial parameters and position and sizes. So we know we've already defined these variables, so we don't have to write in the values ourselves. So for instance, the width of the sub has already been defined as a variable by this name. And then we also have the length as well. So we can just put that in. And then there's only one height variable, so we can put that in there. Now if we hit apply, clearly this box has grown a lot. So I'm going to hit OK, Control D to zoom out, and we can see it's much closer Actually, it's the 10 by 10 centimeters that we hoped for. But it's placed sort of arbitrarily within the canvas with respect to the origin. So we're going to change that. The position of this is going to be dependent on how you want to set up your design. Some designers like to have this origin in the center of the patch or the design, and some would rather have it at the bottom or the center or some other position. We're going to go ahead and do everything with the origin point at the center. So that means it's going to be halfway across the length and the width of this patch. In that case, what you'll do is for the positions in the X, you'll write negative width of the sub divided by 2 so that it's defined by the variables and can change dynamically. And then the length of the substrate as well will be the Y dimension. And then we don't need to change the Z position because we want it to be flush with the plane right there. Now if we hit apply, OK, and reposition our viewing frame with Control D, we can see that the origin is, of course, underneath this box on the bottom side, but centered with respect to its edges. So now we'll go ahead and do the same process, but for a sheet, which will define the patch, the inset gap, and the feed network, and also the ground plane. So using the draw rectangle command will be the easiest way to do this. It's pretty much the same. You click 2 points, dragging your mouse, and then you're able to define the edges of it. Hopefully we can do this all in one go. I'm going to select the very bottom corner right here, start dragging, and you can see it's basically where we want a ground plane to be already. And then I'm going to move over, drag it all the way to the corner here, and then we have our ground plane defined as a sheet on the bottom of the substrate, right where we want it, and we don't have to do any dimensioning. Now it's still good practice to go into the create rectangle command and then change these all to match, so that in case you change the dimensions later on, your whole design will change accordingly. But for the purposes of this, we don't need to do that. Now for every object that you create, you have to define its material so that HFSS will know what to simulate it as. If we click on the box that we created for the substrate, it's currently defined as a vacuum. Obviously, we don't want that. So we double click on this box object and we can change the material to whatever we desire. If you also want, you can change the color and the transparency so that it's something more recognizable. It's especially helpful when you have large, complex designs. So I'm going to click Edit after clicking the material to this drop-down menu. And then you have all of these default materials that are built into HFSS. There's a whole host of them you can look through. If you don't have that, go ahead and click these 2 boxes right here, and then more materials will pop up. I'll just search 5880, and you can see it's already there. I've already added it to the material list, so I'm not going to go ahead and click one of these again, but you'd then be able to change it. And if you hit apply and OK, you would now see that this is a Rogers Duroid laminate material instead of a vacuum. So we want to do the same for the rectangle. We want to define it as a sheet of copper with a finite thickness, but unfortunately, if we look in the create rectangle command, it has no Z dimension, it has no thickness to it. So the way to change that, after creating a sheet, once you have the proper dimensions and you're satisfied and you're not going to change it, you click on the object itself, so this rectangle, you go to Sheet, Thicken Sheet. Now you can give it a certain thickness. For our dimensions, it's going to be relative to a 1/2 ounce copper clad sheet, and so that'll be 0.0175 millimeters. You click OK, and now we have it as a thickened rectangle, so basically a very thin box. And now you can define the material to be something other than vacuum. And in our case, we click Edit and we type COPPER, we can see copper is already defined as a material within HFSS. As mentioned, I've already selected it, so I'm just going to select it from the menu here. And so now we have copper underneath our substrate, and we can go ahead and repeat this procedure for the patch itself to be aligned in the center, and then the feed network as well. I'll go ahead and make most of these additions off screen, and then come back when I need to highlight some important features like creating the inset gap by using the subtract command. So I'll be back when it's time for that. So I've gone ahead and added the patch centered around the origin there, and then the feed network that extends to the end of the board, centered with respect to the x-axis, but shifted a little bit so that it reaches from the edge of the patch to the edge of the substrate. Now I'm going to add the inset gaps, essentially the little cuts the input of the patch itself, and those require a new command that we haven't used before, so we'll go over that together. The first thing you'll want to do is orient things so that we see things from the top, and if you click Orient under the drop-down menu, the top or -Z makes it nice and easy to see in this 2D sort of view. So I'm going to zoom in so that we can clarify what we're seeing, and then I'm going to draw two rectangles one at a time, and let's just say this is my approximation for where the cut mark is going to be. I'm going to go ahead and lay that down, and then we're going to dimension this rectangle to be the dimensions of the cut itself, and then rather than leave it there, we're going to use it as a subtraction from the patch using this subtract command that we currently don't have highlighted. That'll allow us to take away the shape of this little rectangle from the patch, and that's how we're going to define the inset gap of the antenna. So to do that, we're going to have to change some dimensions as usual. So we'll go to this rectangle that we created, go ahead and open it up and change some things around. So the X size is going to be the gap of the inset that's already defined, and then the Y size will be the inset distance. So let's apply and see how that looks. So currently we can see it's the right size and shape, but it's over the feed network. So we need to adjust the origin point, which is the bottom left corner, to go to the left just a little bit so that it doesn't start over the feed network itself. So we wanted to find these positions systematically. So let's think about this. The origin point right here needs to be, right with respect to this origin right here, halfway the distance or the width of the feed, and then one more times the distance of this gap right here. So we'll go ahead and change the X start point to be exactly that. We'll have the width of the feed, and then we'll divide that by 2 and add to it the gap of this inset, which is what we defined as the X size already. Now, if we were to hit apply, we would see it's moved over to the left and in the proper place. We could also change the Y dimension and the Z dimension so that if things need to change dynamically, we can adjust the entire design just by changing parameters. But of course, we're happy with our dimensions and we're going to leave it as it is already. So the last thing we'll do is make sure that this inset gap more closely resembles the real cut that'll be made by a circular drill in a real PCB. So to do that, we're going to add fillets to the interior two corners closest to the center of the patch. Go ahead and hit V on your keyboard for vertice, then hover over these corners, select one, hit fillet, and on each side add a fillet with a radius of 0.125 millimeters. If we hit OK, we can see that it's rounded the edge, and we can apply that same change to the left edge as well, or rather corner, and now we'll have a rounded inset gap that we can then copy to the other side. To copy over the inset gap, go ahead and click on the rectangle, hit through mirror, select some point on the y-axis, and then drag your mouse to the right, and then click again. Now we have two of these gaps perfectly aligned and symmetric around the y-axis there, and we can cut both out of the patch. So at this point, we can start combining and cutting and thickening the copper sheets, including the patch and the feed network and the inset gaps. So to take away the two inset gaps from the patch, we're going to select all three. So let's highlight all three of these. Then we're going to hit subtract, and the blank parts will use the rectangle 2, which is the actual patch itself, and the tool parts, which are going to be removed, will be the two inset gaps that we have. And then we're going to click OK, and you can see that it has been cut out of the patch. And now we want to combine both the patch and the feed network. So we'll take those two objects and use the unite command to combine them into one single object, and it doesn't have a dialog box associated with it. At this point, all we need to do is define its thickness and material. So as previously we did before, we can take this rectangle and under the sheet menu here, go ahead and thicken it so that it's a 1/2 ounce copper thickness, which is 0.0175 millimeters. And then after that, we can double click on it and define the material to be copper. At this point, we're done implementing the design of the patch antenna feed network, substrate, and ground plane, and we can move on to some cosmetic applications, and finally adding the connector to ready it for simulation. So the first thing we'll do is go ahead and round the corners of the substrate so that they're less square, and then we'll add a taper to the bottom of the feed network, and then go ahead and add on the connector. So to add a rounded edge to each corner will be the same process for all four, so I'll demonstrate one. We're going to go ahead and tilt it so that we can see the edge right here. Zoom in all the way to where you can see both the substrate and the copper plane right here. Hit E on your keyboard for edge, and then we'll be able to select both the edge of the ground plane and then also highlight and select the edge of the substrate. So now both are selected. We're going to add a fillet, and this time the radius is going to be 5 millimeter. And now if we zoom back out, we can see it's been rounded, and we apply the same process to all four corners, and we'll have a rounded square for a substrate. All right, so this is what the final substrate with rounded corners looks like. Now we're going to go ahead and taper the bottom of the feed network a little bit. So to do that, you're going to have to tilt it again, zoom in all the way to where you can see the edge of the copper sheet right here. We're going to click on it and add a chamfer. So there's many different types of chamfers. We'll use the left-right distance type. And then for left distance, we're going to select 1.5 millimeters and right distance 5 millimeters. That's when you're on the right side of the feed network. If you hit OK and zoom out, you can see it's been tapered in. Now, when you go to the other side, you're going to have to flip those dimensions because now relatively left and right have been swapped. So we're going to add the chamfer and just reverse those dimensions. And now we can zoom out and see our feed network has been tapered there to receive the pin of the SMA connector that we'll be modeling in shortly as well. So the connector model has been downloaded from the Amphenol RF website, as that is the part number we'll be using. You can go ahead and import 3D models like this to HFSS relatively easily. So if you download it and then go to Model and browse 3D components and navigate to the folder where you have it, you can just click on it and hit Open. We'll type in a password that Amphenol provided so that it can decrypt it, and then allow it to be imported, and then we'll have our connector in the model. Now, of course, it's been imported straight to the origin and it's in the wrong place, so we'll need to do some adjustment to get it where we want at the edge of the board here. So to do that, click on this portion of the model hierarchy with the HFSS design symbol right here, then go to Draw and use these transformational or translational commands. So move obviously allows you to move things. If I click on it, I can have this little black diamond follow the cursor, and then I can click in a different place and it'll move to where I set the second mouse click. Other times you may want to put discrete distances in, and so you can toggle with F3 and F4 between those two versions. Let's say you wanted to move it exactly 1 millimeter up in the Z direction, you could do that via this way. Also useful is the rotate command. Right now it's obviously not positioned properly, so we need to rotate it so that it's pointing away from the patch itself. So I could go ahead and rotate this about the y-axis, and then it'll show me a preview, and then once more about the x-axis. Now it's at least pointing in the right direction. So I'm going to go ahead and reorient this, and then I'm going to take the object and move it down to the edge of the board. So I'll start from the origin and simply put the cursor at the edge, although we have to be in the right mode to do that. So you can see a little outline follows. And so I'm going to zoom in so that I really select the center edge of this feed network. And then now it's been moved, and whoops, we can see that although it's not positionally right in height, the center pin is aligned to the center of the feed network, and the this edge of the connector is mated to the edge of the substrate. So now the rest of our task becomes aligning it height-wise. And there are some ways to go about this faster than arbitrarily moving this up and down. We can calculate distances using the measure tool, which is also on the Draw tab. Let's say I wanted to measure the distance from the bottom surface right here. So I would go ahead and let's say click this corner, and then I would highlight the bottom of the substrate. You could select any point really. I'm going to select one of these corners right here. And if I just hover over it without clicking, I can see the dialog box on the left saying the Z distance is 2.76 and then some more numbers, millimeters. So I'm going to go ahead and remember 2.76 millimeters and then zoom back out. Then I'll select the object, hit move, hit F4 to go to the other version, and then move it up 2.76 millimeters. So now if we zoom back in, we can see it's much more aligned to where the center pin or where these two arms create space for the PCB. And if you're going through this iteratively and you're not sure if there's a minor intersection, let's say the board intersects into the connector body by such a small amount it's not visible, but you want to see if that's the case, you can go ahead and go to HFSS and then hit a validation check, and you'll see an error on the 3D model category if that's the case. Right now we don't have any analysis set up, so we're expecting an error like that. Now, once you've got the connector positioned right, we're going to have to add some solder fillets to make an appropriate model of this. And so we're going to have to add solder that's around this signal pin, and then on the bottom as well, some solder between the ground legs and the bottom ground plane as well. And so that'll be the next task. So when it comes to adding solder and subtracting objects with encrypted models like this connector, we can't exactly use it as a tool, because if we just add, let's say, a box that surrounds this pin, it'll be intersecting and there'll be an error, so we'll need to subtract it. And usually that's okay. If we have two intersecting objects, we can subtract one from the other and create a space, but you can't do that with models like this connector because they're encrypted, because they're proprietary to the company that developed them. So what we'll have to do is create our own envelope of this pin around it, and then use that to subtract away from our solder box. So it won't be too difficult. Just go ahead and align your view to the face of the connector, so it's right here, and then deselect all of these except the this one box right here that aligns your cursor to the center of an arc. These are just helpful cursor snap tools. And then change your drawing plane to the correct plane. Currently I'm looking at the XZ, so I'll have it there. And then begin to draw a cylinder with the draw cylinder command. You can see it's showing me this arc symbol that it's snapped to the center. And then I can draw a cylinder that's basically the shape or outline of the signal pin. And so then I'm going to go ahead and draw this and make sure that it extends just past the edge right here, so that envelops the entire connector pin. And indeed, it looks like it does. And then we can use this green cylinder right here to subtract away from a larger box that will become the solder, and then the two objects won't interfere with each other. So next up, I have this box that I'm going to add. I'm going to change it back to the XZ plane and restore all of my snap functions, and then use the corners of the feed network basically to create this box and make it just enough to cover the whole signal pin right here. Okay, so now we have that there. We can take the box and the cylinder, highlight them both, subtract like we did for the inset gap on the patch antenna, and make sure the tool part is the cylinder, and we don't need to clone it because we want to get rid of the cylinder anyway. All right, so now I know you can't see it, but the interior of the box has a cylindrical hole in it. Now we can literally shave off the edges, highlight the edges. First select E on your keyboard so you're picking edges, and then take these three and give them a chamfer. We'll try 1 millimeter. Okay, so the box has disappeared. That means the chamfer was too big. Do Control Z and then try it again, but let's say 0.5 millimeter. There we go, that looks a little bit better. If the chamfers intersect at some point and they're too large, the entire object will just simply be deleted, and that'll be your sign to back off of that dimension. And the last thing we need to do is make this box solder. Down here it's defined as vacuum, so we'll double click, material, edit, and then you can type in solder and select the one that's most relevant, whichever alloy or lead-free version you like. I've just selected the basic solder so we can have something there, and that's what I'll pick here. So with this top pin solder, you can get as precise as you'd like, or model it in a different program and import it, but I think for the purposes of a rough simulation, it should be more than adequate. So then for the bottom, we're going to do something relatively simple, and we don't have to do any subtraction because there's no intersecting components. So what we're going to do here is just draw 3 boxes and unite them and then shave off the edges once again. So I'm going to snap to the corner here, draw a box that goes up most of the distance, and then just repeat and keep drawing boxes until they fill this whole area basically, and use the edge of the connector as reference points. And then once I've got these three boxes drawn, I can unite them to one object. I'll hit O on the keyboard for unite, and then not select the ground. Make sure I select the box, and then unite them. So now that's one object, and I can take it. I select it properly and assign it a material. I'm first going to take these edges that are along the exposed edge right here and give them a 0.5 millimeter chamfer. That's something a little more understandable. Now, if you go to the chamfer command, you can change actually left and right distance. And so one of these will make the slope steeper, you can imagine. I'm going to assume it's the right distance and give it a try. No, seeming that was wrong. How about the left distance? That'll make it a little more realistic to what it is. Let's try and back off a little bit. So it seems that anything past 0.5 millimeter is too much. That's about as far as we can go. So we'll leave it at that for the moment. And I'll take this box and define it once again as made out of solder. All right, now we have our model materials ready, and we can go ahead and define a analysis and get this thing simulating so we can compare results. So we want to make sure that HFSS has a solution type that's properly set up. Make sure that under that it's HFSS, numeric analysis, and terminal that are selected. Everything else can be left the way it is, just in case yours may have been set up to a different default from the beginning. So now we're ready to set up our analysis. We don't actually have to worry about an excitation because the one already comes inside of the model itself, inside of the connector from the model itself. So we don't have to set that up to input voltage to the antenna itself. All we need to do is set up an analysis. And if we're just looking to get S parameters, namely the reflection coefficient, we don't actually need to set up any boundaries or 3D radiation components to track radiated fields, since all the S parameter data will be located basically within the antenna itself. So under analysis, right click, add solution setup, and then click auto. We can go ahead and do a very high accuracy discrete setup with many points. Let's say from 1 to 12 gigahertz, since our center is around 5.8, so about the middle of that, just so we get the most amount of data. And I'll do a linear step just to make sure that this is in increments of 0.02 gigahertz, so 20 megahertz, and then name it S_param so we know what this analysis was for. And if you want to, you can save fields, but we don't need them to take up disk space because we're not looking at anything that's radiated, as mentioned. So I can click OK, and to make sure we're ready to simulate, save it, click yes, and then do a validation check from the HFSS drop-down menu, and then make sure everything is green, there are no errors. Now we can go ahead and right click and hit analyze, and I'll go ahead and do that. And then after it's done, I'll go ahead and compare the data between this sort of design, the HFSS toolkit antenna, and then a fabricated prototype that's already been made and tested in an anechoic chamber. And so I'll be back to compare those data just in a bit. Okay, here we are. We have all the results, and now we can get to comparing the 3 different versions of the antenna that we have right here in front of us. So on the very right, we have the simulation model that we've built from scratch. This one looks a little different because it's the true simulation model that we've used to gain results. I was merely copying from this design. The prototype antenna is pictured in the center there. This was fabricated and then tested in an anechoic chamber. And then on the very left, we have a picture of the toolkit model, which we made in a previous video. Let's go ahead and look at our reflection coefficient. So plotted on the right there is the reflection coefficient magnitude across frequency of all 3 antenna models. We can see the curves generally agree up to about 5.8 gigahertz, where all 3 exhibit approximately a resonance near -20 dB. Then after that, the curves begin to separate, especially around 9.5 gigahertz. It's obvious that the toolkit model has a higher frequency shift than do the simulation and prototype models. So if we look to the left, we have a table analyzing and describing these results a little more systematically. The prototype antenna has the lowest reflection coefficient at its resonant frequency of -24.5, and the simulation model and toolkit antenna model come in close, both around -20 dB. The resonant frequencies are all quite close to 5.8, but only the simulation model gets it spot on. Comparing the differences between the 3 systematically via percentage, we see that the simulation model is indeed closer by only about 15.8% off from the prototype in terms of its lowest reflection coefficient. And then we have the resonant frequency. Both are only differing by a fraction of a percent, but the prototype is closer to 5.8 than is the toolkit model. This is something we expected, as the simulation model has more features that align it more to the real prototype that we have, including the connector and the thickness of the copper sheets and other things as well. The toolkit model is a little more simplistic and bare, and so will resemble less the results yielded from a prototype tested in an anechoic chamber. So there we have it. I hope this video series has familiarized you with designing antennas from different approaches and using HFSS to simulate them and create 3D models that bring your design and ideas to life. There are a myriad of more opportunities and possibilities that this software can bring to you, even beyond antenna simulation and design. So I recommend you go ahead and explore all that there is. Good luck and happy simulating.